Right. So here, as you can see from the diagram, so before you jump into the mutual inductance, I will encourage you to see the video first. All right. So let's play the video. As you have seen from the video, it is very clear that when that person was bringing that loop and that light close to that permanent magnet, then he can observe that the bulb is glowing, and the moment when he was bringing getting away, get rid of this magnet, then the bulb was dimming. And if you can observe very carefully, very curiously, if you can observe, you'll be able to see that when that magnet was at rest and the person was holding that bulb near the magnet, but the loop was not moving, or it was not shaking, or in other words there was no relative velocity between the loop and the magnet, then you'll be able to see that there is no light. So what does that basically and essentially mean is that when there is a relative velocity between the loop and the magnet, then only we can observe light in the external circuit, although there is no connection. Exactly the similar diagram what I have drawn, and I tried to show you here. Here you can see that there is one loop, that is we will name this one as the secondary loop. Okay, so this is a second, okay, and this is primary loop. Okay, so we name it primary loop, or the first loop. All right, so now this primary or the first loop that is connected with an external power source, and this is a transformer. It is connected over there, transformer. All right, so now the point is this. The question, the purpose behind making this video is this: how can, without having any connection with the direct power source, how can this bulb will glow in presence of a relative velocity between this primary coil and the secondary coil, or in other words a permanent magnet and a secondary coil, without having any connection from where this charge is coming? Or there is no connection. You can see over there is no connection, there is no physical connection. All this wire there is connected with the primary coil. All right, so basically in the experiment what you have seen, that was a permanent magnet. That means that was a producing magnetic north pole and south pole. Exactly the similar thing what you can expect over here. When I switch on this circuit, the primary circuit, then what will happen? The current will begin to flow, right? Let's say for example one particular direction current is flowing. Now as soon as the current starts flowing through the primary coil, then what will happen? The magnetic field line will generate. We know that the solenoid, the property of the solenoid, so the magnetic field lines, they will constitute and they will begin to form in this way, right? So they will go from here and start coming back as a north pole and a south pole, right? So this is what we can expect, right? So this is what we can expect from the primary coil. So direction, if you talk about the direction, then the direction would be this, right? This is the magnetic field line direction, and in the presence of these magnetic field lines, whenever these magnetic field lines are passing through the secondary coil, then secondary coil will experience change in magnetic flux, but only it will change a magnetic flux. But this coil is this transformer is connected with the AC source, if this source is AC or alternating current, or this current direction is always changing, then the flux through this primary coil will always change. And as soon as the flux will change, then the secondary coil, this secondary coil, it will experience a change in magnetic flux. And that is very important, because Faraday said that whenever there is a change in magnetic flux, there will be a EMF, induced EMF, that what we have discussed in the previous video. And this induced EMF is basically is formula is this: if psilin is equal to some constant into d phi dt, right? And this formula can be written by using the formula of the current, and that is basically minus L di dt. Okay, so this is the formula for the mutual self inductance. This is the formula. And now here you can see that directly in the second loop there is no current, right? So we cannot write this formula, because this formula is only valid when the loop has its own current, right? So now if we talk about like current, let's say for example in the primary coil the current is I1, okay, and in the secondary coil the induced EMF generates, and for this induced EMF there is a current, induced current, and this current is, let's say for example, I2, okay. So if that is current I2, so I can write the formula for the induced EMF, and this induced EMF formula for the second loop is this. For the second loop, induced EMF is epsilon 2, I can write, and this formula is minus, and there should be some constant. We are naming this constant is equal to m, and this is basically di by dt. Now the point is that what will be this I? This I will be I2, or this I will be I1. So let's pause the video and think of yourself, and what would be the I2? Okay, I believe that you have tried. So if this is I, then this current in the loop I2, that will entirely depend on the I1. So basically the induced EMF, we are talking about the induced EMF in the second coil, and this will basically depend on the coil number 1. So we can name it I1. So, and this constant could be written as in this form, M2 1. That means the induced EMF due to 2 by 1. Okay, so the induced EMF or the mutual inductance, we can call that in this constant, we can name that mutual inductance due to coil 2, mutual inductance in coil 2 due to 1, we can name it M21, and this is basically responsible for the current in the primary loop. Okay, so in the similar way, if you can dig a little bit deep, then you will be able to understand whenever there is a change in current in the second loop I2, although that is smaller than I1, then this I2 will always generate another magnetic field, right? So if I2 is flowing and is also changing, so that means that this secondary coil, this will again generate a magnetic field. So we are drawing another magnetic field, and which is basically green, as you can see, and these green magnetic field lines are coming and going inside of this primary coil. So what you can expect, this green line will again generate a induced EMF inside of this primary coil. So what does that basically mean is that, so the name mutual inductance itself telling us that there is something which is happening, which we can name it mutual. So mutual inductance, this word mutual, that means that secondary coil, the secondary coil, that the current is happening due to the primary coil, and now this secondary coil, there is a current. When there is a current, there will be a magnetic field, and when there will be a magnetic field, there will be field lines, and these field lines will now penetrate the primary coil, and for which there will be another induced EMF inside of this primary coil, and we can name it epsilon 1, and the formula will be obviously di dt, and that is true. And and there will be a mutual inductance that will be a constant. But in this time I'm just pause the video and just write it down what will be this indices what I have written in the previous case. So if you just I think you have tried, so if you try, then it will be written as in this way: M12, that means the mutual inductance in 1 due to 2. Now this current I should be written as definitely current due to second wear. Now this is the final formula, and this is the formula for this is the idea for the mutual inductance. If you now divide the equation 1 with the equation 2, and you can easily get the mutual voltage, right? So epsilon that epsilon value of the epsilon 1 and epsilon 2 you can easily get if you know the current in the primary coil, right? And also you need to know this constant, because these constants are depends on the number of turns, the material, the radius, and all that stuff, right? But this formula is not ultimate. But for the class 12 standard, this is okay. But this formula is not ultimate. You know that because why? Why? Because you know that one more term should be added. And what is that term? The term is that when there is a current in the primary coil, when there's a current in the primary coil, this primary coil will definitely experience a self inductance, right? And what is the formula for the self inductance? I know that this one will be L1 and this one will be di dt. Now this di dt, this is for its own current, so I can write this one is 1, okay? And for the second one I should write L2, and this will be di dt. I'm sorry, this will be 2, right? So because we have written 2, so this will be 2, right? And this one will be di, and this one will be 1, right? So this is the equation. This is the equation for the final equation for the induced EMF for two coil there which are holding side by side, where we are holding side by side. So this is the final equation. But the astonishing fact is that surprisingly the value of mutual inductance for the primary coil and mutual inductance for the secondary coil, they are equal. And this is this is the equation. And why they are equal? Yes, definitely I'm going to answer this question in the very next video.